I'm Ali Hasanbeigi from Global Efficiency Intelligence. We are a consulting firm based currently in Florida. And this is a presentation. I'm going to briefly talk about the study that we just did on electrification of industry in the US. And why we did this like 6-7 years ago when I was still at Lawrence Berkeley Lab and doing work on energy efficiency, decarbonization, I realized the major lack of information on electrification of industry, especially when we look at the subsector level. And since then, I've been looking to do more work on this. And finally, we got some support from Energy Foundation, and in collaboration with Renewable Thermal Collaborative and David Gardner and Associate, we did this study, which actually we are releasing the report today. So later today, you can go to our website and download the report. It's quite a detailed report. We have done bottom-up analysis for not only subsector level, but also system and technology level analysis for 13 industrial subsectors and how to electrify them and the potential that we have quantified. And also we did survey of industrial plants and with regards to barriers and drivers for electrification, and we developed based on our findings an action plan suggestions for different stakeholders. And we have been communicating our results with different stakeholders already, and we plan to continue doing so in the next few months. So a couple of slides to put things in perspective. US manufacturing energy use, as you can see, goes to different end users, but very clearly this graph shows that around 2/3 of energy goes to thermal related processes, meaning process heating, CHP, or conventional boilers. And majority of energy used there is fossil fuel. So substantial potential there to actually switch to electrification. Another thing, when we talk about electrification, often sometimes people jump into the hard to electrify sector and for example, cement industry and high temperature and basically talk about being difficult to electrify industry. But if you look across different industrial sector, the heat demand profile is very different. And in many industries, actually substantial amount of heat use is in low or medium temperature, which relatively speaking is easier to electrify. With some exception, like a steel industry is high temperature, and we already have a very mature electrification technology, electric arc furnaces. As you can see from graph, for example, the graph on the right-hand side from NREL shows that about 2/3 of the process heat used in the US industry is for application below 300 degrees C or 572 degrees Fahrenheit. So again, relatively speaking, when you have this amount of low to medium temperature process heat, points us to a good potential for electrification. So what we did this, what we call bottom-up analysis for all the sectors that are listed in the table on the right-hand side. Also, we did a whole different scenario for electrification of all industrial boilers in the US. But for the subsector level analysis, we looked at the existing heating system in each sector. And based on the temperature profile, heat demand, how heat is used, we basically look across the portfolio of electrification technologies and see which one is more suitable for each sector. And then we assess the process integration for this electrified technology to get integrated into that particular process in that sector. And based on that, we did some analysis on energy saving potential, GHG reduction potential, and cost. So because of time constraint, I'm going to briefly show you results for 1 or 2 cases that we have done. But again, when you go to a report, you can find much detail about these for all the sectors, including very detailed description of conventional process versus electrified process. So one of the high temperature, we're talking about high temperature industry. One of the high temperature subsector we looked at was container glass. Container glass accounts for about half of the glass produced in the US. It's within the non-metallic mineral sector. So it's an important sector. So this table shows in the middle, the orange line column shows the different process steps for producing container glass. On the left-hand side, we show the conventional process and different heating equipment that is used and the energy intensity in terms of electricity or thermal fuel intensity for each process steps. And the right-hand side is what we constructed, all electric process that based on our research, we suggested that can replace the conventional process. And we have given also the electricity intensity associated with each process step. And as you can see from the bottom row, when comparing conventional and electric process, all electric process use a substantially lower amount of energy in final energy terms. So we get some energy benefit there. And those were the intensity. When we apply that for the entire container glass industry in the US, these graphs show the energy and CO2 implication. The graph on the left shows the change in total final energy use after we electrify the container glass industry. The values are negative, indicating the reduction in final energy use. So you can see this is the total technical potential. So it's we didn't assume certain kind of adoption rate. We just wanted to see what's the total potential. Of course, in reality, the implementation will be more gradual. But in terms of total potential, you can see we get a substantial amount of energy saving if we electrify the container glass industry. And good news is actually for this sector, all the technologies are already commercial. So we need more adoption. And when we look at the CO2, a slightly different story. The graph on the right shows the change in the net CO2 emission after electrification in each year. We have done some projections as well up to 2050. You can see we get some rise in CO2 intensity after electrification. That's because we use the average US grid emission factor. And so basically what we are saying is US grid is not clean enough if we just suddenly electrify. But as we decarbonize the grid based on the assumptions you see in the table below, we then get substantial amount of benefit in terms of CO2 reduction. Another thing to note, this is for the US. If you do regional analysis, which we hope to get support to do down the road, like if you look at certain states where grid is cleaner, this can change. For example, if you do the analysis for the state of Washington, probably immediately you will get your CO2 emission reduction because grid is relatively cleaner in that region. We did some cost analysis for energy cost only. So the energy cost per unit of product, in this case, unit of ton of glass. So this graph shows the energy cost per unit of product for conventional process versus electrified process in 2019 and 2050. Blue is the natural gas cost per unit of product and orange is the electricity cost. So as you can see, the electrified process costs almost twice as much as the conventional process. And that's primarily because in US, as Colin mentioned, natural gas is for now pretty cheap. That may change in the future, probably will change. And electricity is relatively expensive. So in our initial presentation, we got feedback from quite a few people that actually renewable electricity costs is gonna go down more. And we did some sensitivity analysis by showing those error bars, basically those error bars showing what if the price of electricity is 50%, goes down by 50%. So if you wanna see that scenario, basically you compare the lower end of the error bars. And in that case, when you compare the lower end of the error bars, you can see the electrified process is quite cost competitive compared to the conventional process. One other thing to add is here, we did not take into account any carbon price that may come into picture in the future. If that is included, then that blue bar will be higher in terms of the cost of natural gas. So that can also have a significant impact. So that was an example of the sector-specific analysis we did. In the sector-specific analysis, we looked at the end-use processes and then we electrified those. Another scenario is you actually don't touch the end-use processes because they are not at the end of their lifetime or it's complicated. You just go and electrify your boiler in the boiler room. In that case, the changes are mostly in your boiler room and there are some advantages to that. So we developed this scenario where we did the electrification analysis for all industrial conventional boilers in the US. And as you can see in the graph on the left-hand side, in many sectors, conventional boiler account for a substantial amount of fuel use in those sectors. So we basically did the analysis comparing the energy used for the conventional boilers versus electric boilers for all these different industrial subsectors that are shown in the graph on the right-hand side. And based on that, we quantified how much saving we will get and some of the cost analysis. These graphs, a similar graph in this case for the conventional boilers, the graph on the left-hand side shows significant amount of reduction actually you will get if in final energy term, if you electrify the conventional boiler. I don't get into detail because I'm trying to be mindful of my time. On the right-hand side, you will see the same story again because we use the average grid emission factor. If we overnight electrify, we are going to get a bump in our CO2 emission reduction in terms of the change. But then as we decarbonize the grid, we will get significant amount of, you can see it's like almost 100,000 kiloton per year. So a significant reduction. Another thing to keep in mind is, maybe I go to the next slide. For the cost, conventional process or conventional boiler compared to electrified boiler is much cheaper in terms of their energy cost. Electrified cost 3 times almost higher. So that's basically the biggest barrier and challenge. Unless you have much lower cost for electricity, again, our error bars show, then things become more competitive. In some areas in the US where there is renewable energy curtailment or cheaper excess electricity from nuclear or other sources, then conventional boilers may make more sense. One other thing I add here on the cost, these cost analyses are only, again, energy costs. So we didn't compare the capital costs or change in operation and maintenance costs or any other. So if you do a full life cycle cost analysis, taking into account other costs and maybe non-energy benefit, again, it might be a different picture and electrified processes might actually look much better. So that's probably a topic of future study. This graph very quickly show the result for all the 13 sectors that we have analyzed just for the CO2 in 2050, just to show the magnitude of saving we are getting, which is substantial, especially for a certain sector. The highest are for steel, ammonia, recycled paper. For recycled paper, we just electrified the dryer with conventional dryer and replace it with electrified dryer. But as you can see, the cumulative saving can be substantial. Actually, the table I included there, I don't want you to read through it, but just wanted to show you much more detail we have in our report that we have given the saving and CO2 reduction by sector, by year, that you can look into. But if we get the all technical potential and we kind of calculate the cumulative saving, the CO2 reduction is in gigaton scale. Also, things that I do not have time to go over on these presentations that are included in our report are discussion on barrier and opportunities based on our survey. I think you will find some of those findings really interesting. And we have around 8-9 pages detailed action plan where we have given recommendation for government, industry, utility, and technology provider with regards to different items of action plan, whether it's R&D, whether it's economics, education, policy development, etc., that we have discussed in detail in our report as well. So yeah, I encourage you to check our website later today to download the report fresh out of the oven. And if you have any questions, feel free to reach out. Thank you.